Yeah. Yeah, so welcome to the Intro to Deep Learning workshop. This is part of the Dataverse Datathon, and if you guys have any questions throughout this this talk, feel free to just throw it in chat, or even you guys should speak up since we do have a relatively small group here, and just feel free to ask. Right, this should be like a pretty open discussion. But yeah, the main goal of this workshop is just to get you guys familiar with the history, the background of deep learning, and then we'll go into more of the nitty-gritty side of it. So like how forward propagation works, the loss functions, backprop optimization, what these all mean, right? And then afterwards, after we kind of understand the basics, we'll introduce you guys to some different neural networks and some different tasks you can apply these different neural networks into, right? And at the end, we'll be just talking about some downfalls of neural networks and some reasons to be excited about the field, right? And yeah, so I'm pretty sure we're all familiar. Nature often inspires invention. For example, the most classic example is birds. They inspired the invention of aircraft, right? And then you also have like foxes. Foxes actually have very great night vision, right? So that kind of led to the development of night vision goggles. And the same thing for ducks, right? They inspired the invention of flippers. And so, uh, piggybacking off of this, the same can be said for neural networks, right? So, the brain consists of a network of hundreds of billions of neurons, right? That's a lot of neurons. And each of these neurons are connected via what's called a synapse. So it's just like an edge that connects any two neurons, right? And then each of these neurons can fire an electrical or chemical signal through these synapses to connecting neurons. And this is sort of how they communicate. Right? And the idea is, although it's not fully understood right now, the interaction of these billions of individual neurons give us the ability to learn. Right? How we actually learn, it's not very well understood, but they do give us the opportunity to learn. Right? And so that kind of led to the development of neural networks. In the past like 10 years, neural networks have been really hyped up, and it's a really hot topic in computer science. Pretty much if you go into like a computer science PhD or something, you're probably going to be dealing with some sort of neural networks, deep learning, machine learning, right? And so, despite that, the development of neural networks has been a pretty long process. It actually kind of started in the 1940s when a few researchers just thought if you could actually model how neurons interact, right? And they did so using electrical circuits, right? And then, IBM researchers tried to first simulate a neural network, right? And it wasn't really until like 1958 when Frank Rosenblatt introduced this idea of perceptron, right? And so this is kind of the earliest neural network that we still use today. Neural networks themselves, an alternate name for them is just a multi-layer perceptron, right? So it really extends this idea of perceptron that was introduced in the past, right? And then a lot of work has been done since then until where we are today, where these neural networks have billions of parameters, right? And they can do crazy things. I'm sure you guys have all heard of GPT-3. It's a language model, or that's able to sort of lead a lot of the current state of the art in the fields, right? And so let's talk about some motivation and background. So I introduced you guys to this idea of perceptrons. Obviously, it was founded in 1958, and yeah, it was one of the earliest forms of a linear classifier. So suppose we have a bunch of data points or a data feature, so from x1 to xn, right? We just think of this as a vector, and we want to use these features to make sort of decision or some classification, right? And it's going to be binary, so it's either 0 or 1, yes or no, or maybe like cats or dogs, right? And the idea is we want to learn these weights, right? W1 all the way to Wn, and the bias term, such that when you sum up the product of x1 times W1 plus x2 times W2 all the way to xn, right? You sum it up, you pass it through a binary step function, and it's going to output 0 or 1. So what a binary step function is basically if this sum is less than 0 or less than or equal to 0, you output a 0. If it's greater than 0, then you output a 1, right? And what this is intuitively is, we can rewrite this form in like matrix vector notation, right? So it's just a dot product between W, the vector, and X, right? And you add a bias term. And if you equate it to 0, that's exactly just a hyperplane, right? So what we're trying to do is we're trying to find a linear hyperplane or just a hyperplane that separates any two clusters of data, right? And so you can imagine that these blue points are the data points that should be labeled as 0, right? And these red points are the data points that should be labeled as a 1. Obviously, that means that the data has to be linearly separable. What that means is you could draw a line, pretty much, or a hyperplane between the data, and you can separate it, right? That's a very big assumption, but we'll go on to see how neural networks kind of combat this. And yeah, so in the image we just showed you, there are many hyperplanes that can separate the data if the data is linearly separable, right? So in that picture, we just had this black line. However, if you draw this green line, this purple line, or this blue line, they all separate the data, right? And the question that we should ask now is, which one do we choose? And so that's where SVMs come in, right? And the idea of SVMs is just to maximize the minimized distance to each class, right? So you can imagine the two clusters. You just find the point that's closest to your hyperplane from each cluster, and you want to maximize the distance, right? And that's exactly occurs when the hyperplane, or we call it the decision boundary, is in the center, right? And yeah, we use this objective right here, minimize the norm of W, subject to this constraint right here. And the idea is Yj in this case is either 1 or -1, right? And then W, the dot product of W and X plus B, that should output a positive number or like a negative number. And the idea is you just want them to pretty much have the same sign, right? And this is just a half space. This objective itself is quite hard to optimize because you're kind of trying to, the constraint is the intersection of a bunch of half spaces, which is very difficult to optimize, right? This can be done using alternating projection algorithms such as Dijkstra's, but what people normally do is they turn to the dual. If you don't understand that, don't worry. This is just some nitty-gritty stuff if you're curious. And so we have to go back to this idea of linear separability. Linear classifiers are great. However, they are not great in the sense that they can't separate nonlinear data, right? So take the classic example of the AND operation, right? X1 and X2. It's only true when X1 and X2 are both 1s, or they're both true, right? And you can precisely just draw a hyperplane like this. The same thing can be said for OR. However, if you consider the XOR data set, right, it just has 4 points when you just have two variables. It's true when A and B are not equal to each other, right? And so the figure looks like this, right? They're on opposite ends of each other. If you really think about it, there's no way to draw a line that can separate the 2 points such that all the trues go on one side and all the falses go on the other side, right? And so this is where sort of SVMs, all these perceptrons, they don't work anymore, right? However, what can we do in this case? Well, we could take a step back and think about it for a second. In mathematics, oftentimes we have this notion of many linearities can make up a non-linearity, right? So say I give you n lines and I tell you to make a circle, right? Or try to approximate a circle. If I just give you 3 lines, the best you could do is just make a triangle, right? And then if I give you 4, that's a square. And if I give you 5, it's a pentagon, and so on and so forth. However, the more lines you get, the more and more closer you get to making up the circle. And this image sort of just shows you just that, right? And so that kind of gives us some motivation on where can we go from here. Perhaps we could just stack multiple of these linearities. And now the question is, would that be sufficient to model any nonlinear data, right? So what if we just have a bunch of SVMs working together, right? Could that work? And so that's where sort of deep neural networks come in. And we'll give you some motivation and some intuition, and we'll answer that question, right? So to first understand deep neural networks, we're going to first understand this idea of forward propagation, right? So recall the operation W transpose X plus B, W dot product X plus B. Following our earlier remark, let's just stack multiple instances of these operations and see if it works, right? See if it can make like a nonlinear transformation now, right? And so say we have 3 data points, or a feature vector of just size 3, x1, x2, x3, right? These are our features. And then our next layer, we just want to output two outputs, right? So z1 and z2. Well, we could take the same idea, right? Just multiply W with x1, W21 with x2, and so on and so forth, right? Sum them up, right? You get x1. And then you can do the same thing for x2. Notice how these weights are different now, right? This is W11, and then this is W12 down here, right? They should be different weights because Z1 should be learning different features from Z2, right? And now we could rewrite this system of equations, right? This is a very simple example. We could write this using matrices and vectors, right? If you just take this system of equations and put it in matrix vector form, what you get is a 2x4 matrix. This is your quote unquote weight matrix, right? It just has W1 all the way to W31, right? In the first row, and then you also have the bias term. And then what you also have is you have your x's stacked into a vector, and you add this 1 into the vector just so that you can handle the bias term, right? Since we just technically feed it into a 1, and we want to learn the bias term weight here, right? And then if you just do the computation, you can find that this matrix vector product yields exactly the same equation right here, which is very nice. Okay, and so here we have a 2x4 matrix, right? And our next layer we have 2 entries or 2 nodes, right? And so the number of units in the next layer is actually just the number of rows in the weight matrix, right? And since we have 2 here, 2 times 4 multiplied by 4 by 1 matrix just yields a 2 by 1 matrix, right? Because the 4's quote unquote cancel out. And then now we can just generalize this to arbitrary number of hidden units and hidden layers, right? So in the previous example, our first hidden layer just had 2, but you could just stack multiple of these hidden units together. And then after that, once you compute all your z's, you could apply this transformation once again, right? And you can just keep on doing that. And so the question is our transformation nonlinear now, right? However, the transformation in the end is still linear, right? For example, if you can imagine that W3, W2, W1 are your matrices of weights, right? If you multiply them all together at the end, if these are all linear transformations, that still yields a linear transformation, right? So that's not sufficient to model nonlinear data because at the end we just have this really complex linear transformation, right? It still can't separate something like an ETSR data set, unfortunately. And so that's where we have to, turn to activation functions. So the idea of activation functions, obviously successive weight matrices multiplied by the input x would just be a linear transformation in the end. However, what activation functions allow us to do, and a lot of it is inspired by, how the brain works, is it allows us to learn nonlinearly separable mappings, right? And the truth is, most data is nonlinearly separable. The most basic example is the ETSR data set. You can imagine like a lot of these real-world data sets, you can't just draw a hyperplane and separates the classes, right? And so for the remainder of this talk, let us denote the activation function as a. It's a function and it takes an x, right? And so, what I mean by nonlinearly separable and linearly separable, right? So in linearly separable, you can draw a hyperplane. Nonlinearly separable, you can't draw a hyperplane. However, you could draw some sort of nonlinear sort of decision boundary to separate the 2 data points. And inseparability means, no matter what you do, you can't really separate the data. And a lot of this happens when, you can't draw any meaningful conclusions from your features, or there's a lot of noise in your data, right? So you can't learn some sort of decision boundary from that. And so the most basic activation function that's out there that a lot of machine learning textbooks first teach you is sigmoid function, right? So it's just this logistic function, 1 over 1 plus e to the negative x. This blue line plots exactly what that looks like, right? And if you take the derivative, it's just this dotted red line right here, right? And what it does is just basically compresses all values on, if x can be any value, right? However, it compresses it into 0 and 1, right? There's some problems, obviously, right? The biggest one is vanishing gradients. If you look at the gradient function right here, they approach 0 really quickly, right? It's only defined at 0.25 at 0. However, after that, if you input a 6, for example, the gradient is pretty much 0 at that point, right? And later on we'll go on to talk about backpropagation and how optimization works, but this is not good because if the gradients approach to 0, that means it leads to almost no update in the weights, right? And so, yeah, like I said, the gradients of larger and smaller x values approach 0. And this just leads to no updates in the weights. So what can we do? That's where ReLU comes in, rectified linear units. It's a very simple operation. Basically what it does, it just takes the max between 0 and x, right? So it just takes all of the positive values and zeros are all of the negative values, right? And so the derivative is just the stepwise function or just a step function. Obviously, if you're below 0, then the gradient is 0. If you're greater than 0, their gradient is 1, right? And it sort of just looks like this, right? And this is probably the go-to activation function used in a lot of tasks these days, just because it works so well. However, we can observe that the ReLU function is not continuously differentiable, which means, if you look at the gradient at 0, it's undefined, right? Because the gradient is 0 if you approach from the left, and the gradient is 1 if you approach from the right. However, in practice, ReLU works very well empirically, and in practice, we just define the gradient as 0 when implementing. If you get x equals to 0, and oftentimes, x is never really equal to 0, so you don't have to really worry about that case. And the pros of this activation function is that it works actually very well empirically, right? It allows for more discriminability power as values are no longer compressed between 0 and 1. Right? And now this is like the go-to activation for many tasks. And this fixes the vanishing gradient issue that sigmoids had before. And quite surprisingly, continuous differentiability almost everywhere is enough, right? Because although it's not differentiable at 0, it's differentiable almost everywhere else, and that's enough. That's sufficient for it to work well, right? However, there is a problem with using ReLU activation. It's the dying ReLU problem, right? The problem here is that it only outputs 0. The dying ReLU problem occurs when the activation function only outputs 0 for all inputs, right? And so what this means is, say your x's are just a bunch of negative values, right? This would lead to, after you pass it through the ReLU function, it just outputs 0. And if you try to compute the gradient there, it's just 0, right? So if your gradient is 0, you can't update your weights anymore, right? And so no activation means no classification, right? And the gradient at 0 is 0 too, so you cannot update the weights. So what do? There's a bunch of different ReLU variants proposed, right? Such as leaky ReLU, ELU, and CELU. They pretty much make it a smooth function, right? And they sort of just kind of extend it downwards a bit, right? And so now the gradient is defined for like some smaller negative values, right? And if you look at it empirically on the CFAR 10, these activation functions actually do quite well. Here it says that ReLU does quite poorly compared to all of these other activation functions like CELU, ELU, and Swish, right? This does not mean that all of these variants are the best in every single task. It's totally empirical, right? And it depends on your data set and other factors. So just be wary of that. And now we could like go back to what we had before, right? And we could apply these activation functions onto each hidden units, right? And this is very analogous to neurons firing. And so the intuition is whether a new neuron fires or not, and the magnitude of its activation value is very useful in piecing together meaningful features for accomplishing the task, right? So before we had this linear transformation, right? We applied this weight matrix onto X, and then we get Z. Now all we do is we apply this activation function onto each unit individually, and then we get H, right? And then we go back again, we apply another linear transformation, right, with a different set of weights for the next layer, and then once again we apply nonlinearity. And we just do this for however deep your neural network is, right? And the basic idea is with enough of these simple nonlinear operations, we can approximate arbitrarily complex nonlinear functions. And there's a theorem for that. There's also a proof for it too, which is pretty cool, right? And so that's for propagation. Now let's try to understand loss function and what exactly a loss function is. A loss function, in just simple terms, is just measuring error, right? It's just the metric of how bad the model is performing. And so if you want to measure how bad your model is performing, that means you need to have some sort of truth, right? So that means you need a label. You need a ground truth label to compare your model against, right? And oftentimes in supervised learning problems, Supervised learning problems is just problems where there are ground truth labels associated with your data set, right? You need a ground truth label just to measure the loss a lot of the times, right? And the goal of machine learning in a nutshell is just to minimize the loss function, right? It's nothing really fancy other than that, right? And an extension from this is that different loss functions can result in the model learning different very different features, right? So you could be given the same task, but if you use two different loss functions, it might result in two completely different performances. And so the most common or a basic loss function out there is the mean squared error, right? It basically just measures the variance of the model against the the model output against the target, right? And this is really good for regression tasks. So the idea is, y is the ground truth label. It could be any real value, right? Say 100, and then t is your model's output. If t is 0, right? You compute this difference, it's just 100, and 100 squared, that's very large. However, if t is closer to 100, so like say 101, that's just 1, right? 100 minus 1 is -1, you square that, that's just 1. So the loss is lower. So the idea is the higher the loss value, the worse off your model is performing, right? And you sort of just average that across the entire data set, where m is the total number of samples you have, right? And so that works for regression tasks where y is any sort of real valued number. However, in say we have a classification task, right? So like labeling 0 or 1 or yes or no or the cats and dogs. Then we have to turn to the cross entropy loss, right? So this measures the error of a model given that the output of your model is between 0 and 1, right? And the idea is stronger gradient. The great thing about cross entropy loss is that there are really strong gradients. As if you take a look at this example, if your prediction is 0 and the ground truth label is 1, the gradient here is very large, right? And so this could lead to a lot of improvements, and this leads to a very large step in your optimization. And yeah, the idea is Ti is the ground truth label in this case, right? And it's either 0 or 1, and Yi is your predicted probability between 0 and 1, right? And this is very good for classification. This is what it sort of looks like. You can literally just derive this from computing the likelihood function of just a simple what's it called, Bernoulli function. Yeah, and so we have this idea of loss function. Now we have to sort of tackle this idea of backpropagation, right? And now the question is, we're able to measure loss. How do we reduce the loss now? One idea, it's very naive, is to individually tweak each weight value, right? And if the loss reduces, we keep the change. Otherwise, if the loss increases or stays the same, we tweak it again. And we do this for all the weight values, right? This is not feasible because regularly used models have hundreds of millions of parameters. These days, these large models have like hundreds of billions of parameters, right? So this is computationally infeasible, and it's also very naive. And because of the layered structure of neural networks, if you make a change to a weight in one layer, this is not just a univariate effect. It will propagate through the rest of the network, right? So it's a multivariate effect. And now the question is, can we instead find how much to tweak each weight at the same time and ensure that the loss decreases? And the solution is backpropagation, right? The fundamental idea of backpropagation is just from calculus. It's the product rule, it's the chain rule. So the idea is, if j is your loss function, right? The partial derivative of j with respect to z just tells you how much changing z will affect a change in the loss function, right? Now, obviously neural networks are multi-layered, so we also want to find the effect of changing x with respect to the loss function changing, right? And so the question is, how do we compute the derivative of j with respect to x and the derivative of j with respect to y, given that we have the derivative of j with respect to z, right? And this is the simple transformation, right? It's just x times theta x plus y times theta y, right? And then you apply activation function on that to get z. And the question is, how do we calculate this? Well, it's very simple. You just apply the chain rule, right? Because we know that the derivative of j with respect to x is simply the derivative of j with respect to z times the derivative of z with respect to x, right? You can compute each of these individually. The derivative of z with respect to x is nothing more than this right here, and we have the derivative of j with respect to z, which just came in, right? And so an interesting observation is that this algorithm is recursive, right? Once you have the derivative of j with respect to z or x and y, you can compute any other node that forwardly connects to x and y respectively, right? And so now you can pretty much find the change, how much to change each weight. And so let's look at how, now that we have the gradients, how can we use these gradients to do something meaningful? And that's where optimization comes in. So what exactly is optimization? These gradients were computed using backpropagation. The question is, can we use these gradients to solve the optimization problem where we want to minimize our loss function with respect to our weights, theta, right? And in general, deep learning algorithms tend to be some sort of gradient descent algorithm, right? The reason why is because there's large amounts of data, right? And the idea of gradient descent is that it only uses first order information, so just the gradient, as the Hessian is often intractable to compute. If you've taken like calculus courses or even optimization courses, you know that probably the best optimizer out there or method is the Newton method. However, you need to compute the Hessian, which is not feasible a lot of the times, right? So we'll see how we can use the gradients and to see if it's sufficient to just optimize this objective right here. And so let's first get some intuition of what the loss landscape is, right? So say you have a function of two parameters, theta 0 and theta 1, right? This basically shows you how the loss function changes as you change theta 0 and theta 1, right? And the idea is, if theta 0 is like 0.8 here and then theta 1 is 0.6, the loss value is very high, right? However, if theta 0 is like 0.3, theta 1 is 0.8, then the loss value is like very low, right? And we want to find these low values, right? And then we call these the optimal values of theta 0 and theta 1, right? And the main idea of gradient descent is we move in the opposite direction of the gradient, right? So if you compute the gradient at point A, right, it should be pointing upwards. However, if you move upwards, that's going to increase the objective, the loss function, right? So we're going to move backwards instead. We're going to move downwards, right? And so, each iteration, we're going to take a step in the opposite direction of the gradient, and that should hopefully lead us to the minimum right here, right? And so, yeah, these are just some visualizations. If we start at point A and C, and we apply this gradient descent method, it should hopefully lead us to B and D. And this is like a level curve view of what's going on. Just as a disclaimer, the image used here is just a very simplified version of what the loss landscape looks like. Typically, it's not very smooth and easy to optimize, right? Sometimes, most of the times it looks something like this, where there's lots of peaks and valleys, right? It's very easy to just get stuck somewhere, right? And, if you get stuck at a saddle point, the gradient there is 0, so you can't really optimize your function anymore because you can't take a step anywhere. And so that's where, using the Hessian and, higher order information helps. However, that's not feasible. And this image itself, it came from this paper called Visualizing the Loss Landscape of Neural Networks by Lee and others back in 2018. So it's a very cool paper. Yeah, and just as some notation, we'll denote theta as our network parameters, our weights. F is a function of these network parameters, so this is our neural network. And then we'll just denote nu as f prime, which is just the gradients with respect to our loss function, right? And so, vanilla stochastic gradient descent is pretty much exactly what we had before, that we just mentioned in the previous example, right? It's a first order optimization algorithm, and the idea is we just update our weights by subtracting the scaled gradient, right? We have to introduce what's called a learning rate, right? So this is like a step size. It's a scale factor, and it must be tuned. And the performance of your model could vary largely depend on what the value of alpha is, right? And so going back to this example, it just scales your step size, right? So if alpha is very small, you're going to be taking smaller steps, right? That might mean you have to do more iterations just to go to the minimum. However, that might be safer a lot of the times, because if you take like a very large step, you might end up all the way at like point B, right? And say it's not a quadratic term like this, you might end up somewhere else, right? So that's not great. And so, you really have to tune what's called the learning rate. And so, you should just recursively define your update as, your weight at iteration t is just subtracting the scaled gradient, right? And then you just update it like that. And so that's vanilla stochastic gradient descent. Oftentimes that's sufficient, right? That works in a lot of machine learning applications. There are a few more optimizers out there that just exploit a bunch of different things. There's this thing called RMS prop. I won't get into it. And Atom. This is like pretty popular. It was actually proposed by some researchers from UFT. It's called adaptive moment estimation, and it basically just combines SGD with momentum and a bunch of these other algorithms like RMS prop, Allegrad, all of that. I won't get into it, but the most common optimizers these days in machine learning or deep learning is Atom and stochastic gradient descent, right? And all of these packages like PyTorch, TensorFlow, they all implement it for you. And so just to compare how these optimizers perform, this visualization sort of gives you some intuition of how they compare against each other, right? So this is the training cost, which is another way of saying training loss, right? And so here for this author's experiments, they found that Atom converged to the lowest training loss, right? Compared to like SGD, RMS prop, Adagrad, what have you. However, this doesn't mean that Atom's always better. Sometimes, SGD actually could lead to better performance. It's just something that you should play around with on your data set, for your task. And so let's now tackle this idea of regularization, right? First, we have to define underfitting and overfitting, right? It's pretty simple. Underfitting means the model cannot capture the underlying trend of the data. So say you have like a bunch of data points, right, and it sort of makes a quadratic function, but your model learns a linear function. So this straight line here. Obviously, a linear function in this case isn't able to capture the quadratic nature of your data, right? And so we say that the model has underfitted, right? And overfitted is actually the opposite. So the model fits on the training data too closely, and this results in poor performance on the data set, on the testing set, right? And so say you have the same data set, right? However, what you have here is this fancy sort of looking spline, right? That goes through almost every point. However, if you just give it new samples, it probably won't perform well because it didn't learn the actual trend of your data. What you want is a good fit, right? A good robust model that's able to actually capture the underlying quadratic trend of the data, right? And regularization methods are just methods to help you achieve this good fit and robustness, right? And so first we have to understand that, how do you train a deep neural networks? How do you train a deep neural network? You train it in batches. So what exactly is a batch? This just means you input multiple samples from the data set at once, and you train it in parallel, right? So yeah, you're just basically running multiple instances of your neural network in parallel, right? So say we have this example where we have a batch size of 4. We're basically trying to classify these images. What we're trying to do is we input 4 images at the same time, right, into the same neural network. We run it in parallel, and it outputs different outputs given the respective image. And doing so is actually very beneficial because it stabilizes optimization and lets you use cool regularization techniques like batch normalization. And the stochastic gradient descent, the stochastic part comes from just taking the expectation of your gradients across your batch, right? So by using this, you're able to sort of get a better estimate of which step to take in, which descent step you should be moving in, right? And so we have to introduce this idea of L1 and L2 regularization. It comes from a lot of optimization statistics. Basically, L1, you just add the L1 norm, right? So you just take the absolute value of all your weight terms and you sum them up. And the idea of L1 is it promotes sparsity. It has multiple solutions, and it's very good for feature selections because it promotes sparsity, right? It basically suggests that you want to find weights, you want to find W's that just are kind of close to 0 or at 0, right? However, the problem with this is because it's very sparse, it has very sparse solutions, it's unable to learn very complex features. On the other hand, L2 is another method to prevent overfitting. you know, it only has one solution and it's able to learn complex features, right? And basically just add a quadratic term instead of taking the absolute value. And what does this sort of look like? It's sort of like this. So by adding this absolute value, you sort of get this, I guess it's a diamond, right? And then H is sort of your, I guess, hyperplane, right? And the hyperplane and your diamond intersect when x1 is 0, x1 is 0, right? So that's why it promotes a sparse solution, because here x1 is 0, x2 is not 0. If you take a look at L2 regularization, it basically just creates a ball, right? And basically they intersect when it touches the ball, right? And there's only one solution because, you know, hyperplane will only intersect with this ball at one point. And so yeah, that's sort of intuitively what it looks like, and hopefully this gives you some intuition of why L1 promotes sparse solutions, just because they intersect when either x1 or x2 is 0, right? And you can generalize this for an arbitrary number of x1s and x2s. And so the first I guess the second regularization technique that's used in deep learning is called dropout. The idea is, you know, every neuron is removed with probability p during each iteration. You know, oftentimes we set p equals to 0.5. So, you know, we're basically just taking half of the neural network at each point. And this reduces overfitting just because it reduces the number of parameters of the model, right? This forces the model to learn more robust features with less parameters. And with more parameters, the model can easily pick up noise and shortcuts during the training that may not generalize well. And I guess to give you some more intuition, it just makes sure that, like, you know, the model doesn't just focus on like one node specifically, right? Because at each iteration, we have a random, we just have a random neural network, right? And so hopefully it should spread out all of the learning throughout every single node rather than just focusing on one node specifically, right? And there's a difference when you're training and testing using dropout. During training time, you know, you have to remove each neuron with a probability p, right, for each iteration. And so this just means that the neural network used at each iteration is different. However, you know, at test time, you have to use all your neurons, and you know, we can't just take a random sample, random, you know, a combination of neurons to use. Instead, what we do is we use all the neurons and we just scale all the activations by a factor of p. And the intuition behind why it works is that it counts for missing parameters during training. I don't think there's too much theoretical grounding as to why this works. However, it works very well empirically, so that's why we use it, right? And so the idea at test time is that the neuron's always present. However, we just scale the output just by a factor of p. And so if you use dropout versus not using dropout on, let's say, MNIST, this is where this image is from. You know, without dropout, the classification error is at like around 1.75%, and with dropout, it sort of converges to 1% consistently across the board, right? And this was taken from the paper, the dropout paper itself. Yeah, so it shows you that dropout does work as a regularization technique, and it's able to learn more robust features. And so another common technique that's used is batch normalization. It was originally hypothesized to combat this thing called internal covariance shift. And what internal covariance shift means is a change in distribution of the input variables during training and testing. This was actually proven false from a group by MIT in 2018. However, we still use it because it works so well empirically. A lot of people just say it's sort of just black magic, right? And the idea is for each sort of neuron, you just scale it by, you just normalize it across your batch, right? So you have this batch mean for your neuron, and you have this batch variance, and you just scale your neuron term, your activation value, right? And so, yeah, like I just said, it normalizes the post-activation value of a neuron across the batch. And there's a difference when you're using this during training versus testing, right? During training, you have a large batch, right? You're able to calculate the mean and standard deviation, so you're able to sort of just normalize it, right? However, during testing time, a lot of the times what you're doing is you're just inputting one sample at a time, right? So there is no batch, right? And so you can't calculate a batch mean or batch standard deviation because that value is just undefined, right? Because the variance will be 0, the mean will just be itself. You have 0 divided by 0, that doesn't lead to anything, right? And so what do we do instead? During training, what we do is we keep track of like an estimate of, you know, what the true mean and standard deviation should look like, right? And we just use the exponentially weighted averages of the of the means that we calculate and the standard deviations at each iteration. Right, and we don't optimize this because it's impossible to optimize, since if you're curious, it contains the gradients from previous batches and time steps. However, we use this to estimate the universal mean and standard deviations just by using the training set, and hopefully this mean and standard deviation should generalize well to test data. Right, and so like I said, once we calculate these values during training, we're able to use these to scale our activation values during testing. And so why does it work so well? I guess, it's robust to parameter changes in the previous layer because now every single neuron is just sort of treated as a standard Gaussian, right? And it forces independent learning of each layer just because, each neuron is a standard Gaussian, right? And so if you change some weights in the previous layer, that hopefully shouldn't change, the activation values of your next layer just because it's still a standard Gaussian. And so yeah, so now I kind of gave you guys a TLDR of deep learning, sort of how it works. In a very basic form, what we just saw were feed-forward neural networks, right? So just the standard MLP structure you just saw. However, that's not very used. That's not used very often in a lot of tasks. It doesn't actually perform that well oftentimes. So we have to talk about some common architectures that people do use and how and what type of data you could use it on. So the first one is convolutional neural networks. You've probably heard of this term before. Basically, instead, now the weights are now a kernel that slides across the feature map. What I mean by kernel, you could think of it as just like a small a matrix, like a 3x3 matrix, for example. And what you do is you just slide this matrix across your feature map or your input image, right? And instead of calling all of the intermediate hidden units, we just call it a feature map in the context of convolutional neural networks. Right, and the reason why you want to use like sliding window these kernels is just due to the reason of weight sharing, right? Because objects and features and images can appear at multiple locations and their position may change, right? These convolutional operators allow the weights to be invariant to location. If you rotate the image, it should still work. All right, and if you're curious more on convolutional neural networks and just computer vision in general, you could check out our reading group videos on our YouTube channel just for more breadth. And yeah, some common CNN architectures are ResNet, right? So it's this down here, DenseNet, DeepLab V3, right? It's a very great segmentation model. UNet, it's used a lot in medical image segmentation. And then temporal convolutional neural networks. These actually aren't used for images. They're actually very good for autoregressive data, right? So like time series data, TCNs are used sometimes, right? And I just listed out some of the common architectures you could use. Depending on what framework you're using, if you just type it in on GitHub or something, you could probably find a very boilerplate implementation of it. For your either your framework or for your data set that you're using, right? So the next one is recurrent neural networks, right? These are used a lot in like NLP tasks, so natural language processing, and a lot of data that are just sequences, right? And so what it does is it uses internal state memory to process the variable length sequences, right? So what we do is we pass, so like say we have the word jazz, right? We first pass in J, right? Passing through our weights, the weights output some hidden vector, some output H0, and it also outputs this thing called internal state, which is memory, right? And you feed that in, you loop that back into the weights again, right? And then you pass in the next input in the sequence, right? And the idea is the weight, this hidden memory, keeps track of all the other information that you've already processed, right? So by the time you're at Z, this hidden memory here should capture features learned from J and A, right? And this is very good for temporal and sequential data. For example, people use LSTMs for stock price prediction all the time. And yeah, it's very good for natural language processing because it's a bunch of sequences of data, right? So for example, some tasks you might do are semantic understanding, name entity recognition, just to name a few. Some common RNN structures out there are LSTM, so long short-term memory. LSTMs basically improve RNNs for a number of reasons. I won't get into it. And another one is gated recurrent unit. So it looks very similar, and the principles are the same, right? And you can use these and stack them up to build transformers, right? And then this thing called BERT that was proposed by Google a few years back. But yeah, there are actually lots of implementations of transformers online. There are lots of APIs. So if you use that, training a transformer from scratch is probably not the best idea because it uses a lot of compute, right? However, there's a lot of pre-trained transformer models out there that you could use as just like an API or something. So for your project, you might be interested in using transformers. So another one that's not really talked about a lot is graph neural networks. These neural networks are just neural networks that operate on graph structures, right? So a graph structure is just any data that has a bunch of nodes, and then between each nodes it also has like an adjacency graph. So it just describes the connectivity between each of the nodes, right? And the idea of these models is that it models the dependencies and interaction between nodes in the system via message passing. And just to give you some intuition of what this is good for, it's really good for recommendation systems, right? So let's say each node is like, I don't know, like a person, right? And each edge just might mean like how similar are these two people to each other, right? So if they're very similar to each other, we could take the recommendations of one person and give it to another person, right? And so Uber Eats, surprisingly, they actually use a deep learning method. They use this thing called a graph stage. It was a method proposed a few years back. And yeah, it's pretty cool because it's showing that a lot of these big companies are actually using these deep learning solutions nowadays to do things that we weren't able to do before. Another good domain where it's graph neural networks shine in is drug protein interaction and drug discovery. Actually during the start of COVID-19, there were actually a lot of papers that use graph neural networks because everyone was trying to discover this new drug to hopefully cure COVID-19, right? Or cure COVID-19 if you had it. And it's also good for link prediction, right? So it's predicting whether two nodes, link prediction is the task for predicting whether two nodes have a link or edge. So it's kind of similar to recommendation system where you're predicting if two people have similar tastes in food. And some common graph neural network architectures, they should actually say GNNs, are graph convolutional neural networks, right? That's the most commonly used one. Graph attention networks, message passing neural networks, and ShebNet. These are some images to show you on what it sort of looks like. I won't get into it. However, if you Google any of these, there's lots of implementations on GitHub, that you could use if your data is sort of a graph structure. And the last one is more like a field. It's called generative models. So rather than prediction, generative models just generate new data, right? Because before we had like, say, we were given an image, we want to predict like a label, right? Or given an image, we want to segment out the pixels. Generative models instead is given some random noise, we want to generate some sort of distribution. We want to generate images, for example, right? And generative models are actually really good for density estimation. More specifically normalizing flows, are really good for density estimation. It's very good for image synthesis, real-time image editing, and generating new training data. So I just mentioned generative models because I feel like generative models are a really cool datathon project to work on since it is quite flashy, I'd say. And so there are some classes of generative models. The first one is autoencoder. This is probably the simplest one to understand. So some common ones are variational autoencoders, conditional variational autoencoders. And then you have GANs, generative adversarial networks. You've probably heard of this term lots of times, right? And so common ones are Wasserstein GANs and dataset GAN, which was the implementation of a GAN to generate new training data. And so there's also normalizing flows, real MVP, made, sauce flow, and these are just good for estimating the actual density of a data set. For a datathon project, I don't think it's too important. However, this has a lot of like real-world statistical applications, right? And the last one is just diffusion models. I won't get into it. A good application of it is SDE edit, and basically it's just a method to just edit, any image that you already have. And so this image right here just shows you this idea of image synthesis, right? And so say we have like a destination, so a bunch of images of people, right? And we have a source image, right? We want to combine these two images together such that they form this new person, right? And this image sort of shows you how it works. This was actually used. This was actually done using a GAN, and so this kid, for example, in the style of this lady, would look like this, and yeah, so on and so forth. So it's pretty cool. You could synthesize two images, combine to form a completely new image. I think that would be a really cool datathon project. If you guys need some ideas. And so, we should talk about some of the downfalls of deep learning, because I do feel like it's a little hyped up these days. Um, and so the biggest problem with deep learning, I think, is just that it's very data hungry. It requires a lot of training data to generalize well. So if you have like a really small data set of like 100 data points, I wouldn't use deep learning. I'd probably use something different, like SVMs, for example. And another issue is that it's not very interpretable, right? Just because, in the feed forward neural network example, we just saw all of these, we pass in weights, right? We pass in, and then we apply this activation function, then we pass in another set of weights. It's very hard to kind of define what every single neuron is learning and what sort of every weight is doing, right? And so this is a very big problem for commercializing its usage. For example, in the medical field, a lot of times you want to understand how your model got to a certain decision, right? That's very important too. However, if you can't interpret it, then you can't really use it, right? There are methods like in computer vision to do it. For example, saliency methods, if you're curious. However, in fields like natural language processing, it's a little harder, I'd say. Another problem is that it's very easy to overfit on your data's domain, and this kind of goes into data hungry, right? Because if you don't have a lot of data, your model will probably just overfit on your data, right? And then, so if you give it new samples, it won't learn the actual trend of your data, right? And then we call this field domain adaptation, where if you train your data on specifically one type of data, so like let's say two common data sets out there are CFIRE10 and like maybe ImageNet, right? They're two different image data sets. The images look kind of similar, albeit they're different dimensions. Say you train a model on ImageNet, and then you test your model on CFIRE10, it probably won't do so well on CFIRE10, sadly. And so, domain adaptation is just a field where, how can we transfer our knowledge from training on one data set onto another data set and make sure it performs well on a different data set. And lastly, I feel like a lot of problems actually do not need deep learning. Deep learning is a very easy solution to things sometimes. Some problems, are just unsolvable using deep learning. So just don't forget about your classical statistical and optimization algorithms, right? And here we just have this simple meme or this funny meme. I'd say, in statistical learning, if your thing's not performing so well, if your model's not performing so well, you probably do something sort of complicated. However, the running joke in deep learning is if your model is not performing well, just add more layers or just make it deeper or wider, and hopefully it works. And sometimes, funny enough, it does work sometimes. And yeah, there are actually quite a few reasons to be very excited about machine learning and deep learning. The first one, you've probably heard of it. Recently, I think it was GitHub, they released this thing called Copilot. It was powered by OpenAI's GPT-3 model. And basically what Copilot does is it just auto-completes code, right? And what I mean by auto-completes code is you just simply write a comment just detailing the function you want to write. So I want to write a function that computes all the primes up to 100, right? You write that as a comment, and then it will just autocomplete with the function itself, which is pretty crazy, right? And so yeah, this is kind of a life hack, I'd say. I'd say a lot of my friends nowadays, they're using this just to complete their CS assignments, which is kind of funny. And yeah, I think this is available for public use now. Yeah. And then there's OpenAI 5. This happened like I think back in 2018 or something, or 2019. OpenAI just basically trained this model, this large model, using LSTM's proximal policy optimization, a bunch of these techniques, to train just this team of players that are able to beat the best players in Dota 2, which is a game very similar to League of Legends, if you're familiar with that. Right, and just to give you some idea of how hard it was to train this model, it took around 100,000 CPUs and 256 P100 GPUs to train. Right, nowadays these numbers actually aren't too bad because I think like Google Brain and stuff, they're releasing papers where they train on like thousands of TPUs, and I'm like, yo, how is anyone supposed to recreate, or yeah, how's anyone supposed to recreate your method? Because we don't have thousands of TPUs like Google does. And yeah, this is what the OpenAI 5 architecture looks like. It just combines a lot of the principles we just mentioned and puts it together. But you can imagine how this is very difficult to train, just because it's so deep and complex. Another one is few-shot adversarial learning of realistic neural talking head models, and this was published by Samson AI like back in 2019, I believe. I'll just play this video, and you guys should get the idea of what's going on. So yeah, you just basically feed in an image, and it should be able to animate the image doing stuff, which is pretty crazy. Then this is like very useful for like say deepfakes or stuff like that. And yeah, I guess the idea of this is actually like a field where people just try to animate, I guess, images. The reason why this work was so like monumental, I'd say, is because they did it using this few shot method where you use very little data. So that's pretty cool. And then another use case of machine learning was Google AI's lung cancer detection. Basically, this was published back in 2019 as well. They trained a large-scale CNN to detect whether a patient has lung cancer or not, just from, I think it was a CT or MRI scan. And it performed pretty much better, on par or better than clinicians. So that was pretty cool, and it had like a lot of media attention. And I guess the last one is AlphaFold. If you aren't aware, this came out like last year and the year before. Yeah, it came out last year, and basically it kind of solved the quote-unquote protein folding problem. And this is pretty much an unsolvable problem in biology up until like AlphaFold. This was part of the Critical Assessment of Protein Structure Prediction Challenge, CASP, that's held every 2 years. And yeah, just to give you some idea of like how well AlphaFold, this deep learning solution, does, this graph shows you like the score, right? Out of 100 is the best score you should get. In the previous years, you're able to only achieve around 40, I guess 40% accuracy. However, once AlphaFold and AlphaFold 2 came in, they really pushed that number to around like almost 90%. Right? So this is pretty cool. It's a deep learning solution to predict how proteins would just fold, and apparently that's a very useful tool to have in biology and like I guess chemistry. And yeah, I guess that sums up my talk and workshop on deep learning. Hopefully that gives you enough knowledge of what's out there in deep learning and what tools you can use, and sort of how these deep learning methods are trained and optimized. So I'll be happy to take any question now. All right, cool. Let's see, chat. Thank you. Yeah, thank you for listening, guys. Yeah, I guess like some reason. No questions, but it's very informative. Okay, cool. I'll share the slides in the Discord server after, because I know that stuff like this, it might be very useful for you guys. There's a lot of great resources out there on GitHub. You just type in transformers. There's I want to say like thousands of implementations. You just take their code, since a lot of deep learning methods are just very boilerplate, and just apply onto your data set. I remember, I think Jack in his workshop, he also gave a lot of good resources using Keras, another deep learning framework. I'm more familiar with PyTorch. However, you could choose PyTorch, TensorFlow, Keras. And yeah, you should check out his workshop too. There's like a YouTube recording, and there's also like he shared his Google Colab notebook with us. So yeah, you can take a look at that too. But yeah, I guess thank you for attending.